So this talk is not with my UD hat on, but with my hat on where my role is the Director of OpenACC User Adoption. So my job, which I love to do, is to tell people about programming models, how wonderful the programming directive-based model is, what is OpenACC, how do you use this on scientific applications, how do you migrate them, and how do you do step by step. So that's what I do, and people are interested, I tell them more, and sometimes they would like to join OpenACC as a member, like SUSE. So SUSE is one of our newest OpenACC members, and that's why I'm here, giving you an introduction of why did they become a member and what are the cool things you could do. So OpenACC, as a brief background, it's a directive-based parallel programming model, and the idea behind using this model is to be able to do cool research without spending a ton of time programming. So the motto is more science, less programming. And to give you in a nutshell, I can say that back in UD, we took a chemistry code, which was serial. We spent 10 months on it just to parallelize it, profile it, optimize it, and we were able to bring 14 hours down to a minute using OpenACC directive-based programming models. And Mauricio is one of the two students, along with Eric Wright, who did this with mentorship from PhD in chemistry department, computer science and chemistry department. So the takeaway is directives are not magic, right? So you need to spend time to use it. You need to spend time to iteratively improve your code. And if you do that patiently, you're going to get rewarded. So it's an iterative process, so take your time. So this slide is to give an idea of the kind of codes that have been ported to OpenACC. And this is a list of code that's Ellis Dalton, Flash, GTC, XGC, and E3SM, which are 5 of CAR codes. And CAR is a program, part of the OLCF, Oak Ridge National Lab program. It's Center for Application Readiness. I don't know what the other A stands for, but these are the 5 CAR codes that use OpenACC for performance and portability. And you would see a quote from Jack Wells, who's Director of Science for the Oak Ridge Leadership Computing Facility, where the takeaway here is on Summit, which is the fastest supercomputer right now, with IBM Power 9 and Volta 100 GPUs, 5 of the CAR codes are using OpenACC to show a new level of science capability by achieving significant performance results, making practical, newer scientific opportunities possible. This is a slide that shows the number of applications that are currently using OpenACC. To highlight some of the commercial codes, there is Numeka, computational fluid dynamics, Synopsys, Gaussian is a quantum chemistry code, ANSYS Fluent, ADS is aerodynamics, computational fluid dynamics code. So these are production level commercial codes that are using OpenACC right now, besides the 5 CAR codes on Summit itself. And this is a bigger list that gives you another idea of the other applications, for example, visualization of molecular dynamics. And we saw Gaussian earlier. We didn't see Sanjeevni, IBM CFD, MPAS is a weather code from NCAR, National Center for Atmospheric Research. VASP is from University of Vienna, Cosmo, and Quantum Espresso, MAS, and IBM CFD, and so on. So none of these codes were done overnight. So the message to here is, you start applying, you go in an iterative process, you profile, you analyze, you optimize. You don't like the performance results you see. So you go back and redo all these steps enough to be at a phase where you're happy with what you're doing, which means you have seen some performance numbers, some portability, productivity metrics as part of your code. And this is a slide that shows you, the kind of different things that's happening with OpenACC. For example, 3 of top 5 HPC applications, 5 of 13 CAR codes. A number of accelerated applications have grown over the past 3-4 years. And this particular box here is about the OLCF flagship hackathons, GPU hackathons that has happened over a period of times over the past few years across the continent. And one of my students sitting right here has also been a mentor in one of these hackathons. And via these hackathons, we have trained over 700 domain experts. And these are experts that come with science background, not much of a CS background, but they come to these hackathons with a massive code base, and they want to be able to parallelize it and port it on heterogeneous systems. So we are sitting in round tables, probably a team of 5-6 domain science plus 1 or 2 computer scientists, and 2 mentors per team looking at the code, trying to profile it, trying to find where the computational hotspots are. And this is a 5-day thing, right? It's not 1-day thing. So in the first day, you're trying to get your code on the machine. The second day, you're like, oh, so now I need to profile it. Third day, you have the hotspots, and people who have never used OpenACC starts to get trained as to how do I plug in these directives in a sequential code base. And then you go about in full circle, right? You try to parallelize it, you optimize it, reprofile it. So that's what the hackathon is all about. It's been extremely successful. And I started a Slack channel sometime in SC 2016. So we started off with no members, and now we are over 600 to 700 members in Slack channel, where it's a communication channel open to everybody. So completely anybody and everybody can join, where we get all sorts of questions, right? So what is OpenACC? Or how do I teach OpenACC? Or how can I use OpenACC? Or where do I find, education materials to teach OpenACC in a university setting or an institute setting? Or I'm running a hackathon, help me promote. Or somebody posts a code snippet and says, oh, this is giving me a compiler bug, how do I fix it? So some of us on the Slack channel jump in and try to help these application developers fix their code, report compiler runtime bugs, and be able to tell them that, look, these are the things you did right, these are the things you did wrong, that kind of stuff. And PGI Community Edition, that is still updated, even more updated, so you can see the amount of downloads that have happened. And this is important, especially for the university setting, because Community Edition is free and licensed, so it is at no cost. So you can download it. Like when I teach, architecture to my students, and if I want them to play with a compiler, I tell them, hey, look, go to the PGI Community Edition website, download it, be it Windows, be it Linux, or any, operating system. They are able to download the compiler, run a Hello World within that 75 minutes. And that's what is made possible by the Community Edition. And there was a release 18.1, the 18.10 released this week on Monday. So PGI 18.10 is released, and it's 2018 October. So that's how they, they coordinate. So this is the new OpenACC 2.7 specification that was released this week. And if you walk by the PGI booth, or you can come to UD booth, we have these little reference cards that we can give away to you, where there were 4 features added to the OpenACC specification, and all these 4 features have been repeatedly asked by users who are using OpenACC. These are features that they say, oh, do you have a self clause, or what do you do when memory is read-only, right? How do you communicate to the compiler that this particular memory is read-only? So that's a read-only modifier in the copy and cache class. Self clause is on the compute constructs, which is using both multicore and the accelerator in the same program without needing to dynamically change the device itself. Arrays allowed in reduction was another important feature that the users asked, and some of these features come up during the hackathons. When application developers are sitting in circles and they are trying to find out, okay, that I need this particular feature, else I'm going to do a lot of workarounds or rewrite my loop. So if I don't want to do that, do you have a directive? So there are compiler developers sitting in that hackathon, so we make notes and we talk in our weekly telecons, oh, this particular user asked for a directive, and this was the case study that the user brought on board, things like that. And default clause on the data directive apply to any compute construct that's lexically contained and connected in data construct. So these are the 4 features, and if you go to the OpenACC organization website blog tab, you would see Michael Wolf has written a nice blog, so you can go take a look at it to get more details on each of these topics. So welcome SUSE on board. Oh, they have joined OpenACC organization. Yes, I say gays behind. That's fantastic. So welcome on board. This is fantastic for OpenACC as well as I'm sure for SUSE too. We also have 2 new members, CDAC Pune, India, and Osaka University. And you can see a variety of both academia as well as national lab members as part of OpenACC organization. So we are looking forward to do cool stuff with SUSE as part of this new membership. So I wanted to bring to light the number of hackathons that will happen next year. So you can see about 4, 6, 8, 9 of them. 3 more dates are not fixed, so we don't see them in the list. But you can see it's starting from KISTI, which is South Korea, Germany, Australia, MIT, Princeton, NERSC Lab, Sheffield, Brookhaven, and Oak Ridge National Lab. So it's across the continents, across different countries and different dates. We started off with 2 per year, and now it has grown up to 15 per year. We started with 10 mentors, and now we have students like my group. 4 of them go to these different hackathons and act with their mentor hat on. They try to get codes on GPUs. So it's growing really fast, and it's growing in the right direction. Well, that's what I had. So I'm happy to take any questions, or you can write to me. I'm Sunita Chandra@udl.edu. If you have any questions, feel free to contact me. And thank you for listening.
Awesome.